Hey, you ever feel like time plays tricks on you?
How do you mean?
Like you're waiting for something exciting and every second feels like an hour, maybe.
Oh, yeah, definitely. Waiting for exam results, maybe.
Totally. Or a really boring meeting, but then, you're having an amazing time like on vacation or something and suddenly the whole day's just gone. Poof.
Vanished. I know exactly what you mean. It flies by.
Well, what if that wasn't just, in your head? What if time itself and even space like the actual reality we live in could actually stretch and squeeze?
Ah, you're leading us right where we need to go. That's a fantastic way to dive in because it hits on something huge that we just, well, we take it for granted, don't we?
Right. Our gut feeling is time is just tick-tock, steady for everyone.
This constant universal beat. But yeah, the ideas we're going to explore today, they really they challenge that assumption deep down.
Absolutely. I was thinking about this time I was waiting for some news,
Right.
and this was ages ago. It honestly felt like slow motion. I swear the dust floating in the sunlight was moving faster than the clock.
Huh. I can picture that.
But then, like last summer, I got completely sucked into this jigsaw puzzle.
Hmm.
One of those impossible ones.
Yeah.
All blue sky pieces.
Oh no.
And suddenly it was like midnight. The whole day just disappeared. It makes you wonder, right? Is there more to it than just how we feel about time?
And that is the perfect jumping off point for our deep dive today. Because we are going deep into the revolutionary ideas of Albert Einstein.
Einstein. Okay, so you hear the name, you picture the hair,
Yeah.
the EMC, and the genius,
Yeah,
right?
exactly, the icon. But we're actually going to go back a bit to the early days, to the young guy working in a patent office in Switzerland.
Right. Not exactly the established professor in a big university lab.
No, he was this patent clerk who just dared to think about the universe differently, completely differently than, well, pretty much anyone before him.
Yeah, I was reading some of the background. Apparently, he wasn't the easiest student either. Some professors found him a bit, well, maybe a little grumpy or cutting.
That's the story, yeah. But while he was looking at other people's inventions, his own mind was cooking up these ideas that would just completely flip our understanding of space, time, everything, really.
It's kind of amazing. This, like, outsider changes the entire game of physics.
It really shows you, doesn't it? Those big aha moments, they can come from unexpected places. Often it's about questioning the stuff everyone else just accepts.
Like asking, but why? About the basics.
Exactly, and that's what Einstein did with relativity. So our mission today is to really dig into the core ideas from his theories, special and general relativity. We want to make them clear, maybe even intriguing,
Definitely intriguing.
and show why these concepts, even though they're over a century old, still shake things up. Foundational stuff for physics, even philosophy. We'll try to skip the super heavy math and focus on the concepts, the aha moments.
Okay, sounds good. So where do we start? You mentioned light.
Yeah.
Something about the speed of light got him thinking.
Yes, that's the linchpin, really. There was
Yeah.
this experimental fact emerging that was just weird.
Weird how.
Well, normally speeds add up, right? Think about like a police car chasing a speeder.
Okay.
If the speeder's doing 90 and the police car speeds up from 0 to, say, 80, the difference in their speeds shrinks. It goes from 90 down to 10 miles per hour. They're catching up.
Makes sense.
Yeah.
Common sense, yeah. If I'm walking slowly and you jog past, your speed relative to me is just the difference.
Exactly. But light just doesn't care about that.
Doesn't care.
Experiments showed again and again that the speed of light in a vacuum, empty space, is always the same, about 186,000 miles per second. Always.
Okay, constant. So
So imagine you're standing still, you measure that speed, fine. Now imagine you're in a spaceship zooming along at like half the speed of light, 93,000 miles per second, chasing a beam of light.
right, I'm trying to catch up to it.
Common sense says you should measure that light beam moving away from you at only half speed, right?
Yeah.
186,000 minus your 93,000.
Yeah, that's what my brain says. The difference.
But nope, Even in that super fast spaceship, you'd still measure the light beam racing away from you at the full 186,000 miles per second.
Wait, what? How?
Yeah.
How is that possible?
It's bizarre. It totally breaks our everyday intuition about adding and subtracting speeds. It's like the universe has this absolute speed limit, and everyone, no matter how fast they're moving, measures that limit as being exactly the same number.
That is, yeah, bizarre is the word. So Einstein didn't try to explain why it was constant at first?
Not initially, no. He
Mhm.
basically just said, okay, let's assume this weird fact is true. Let's take it as a fundamental principle of how the universe works. And then he started figuring out what that assumption means for everything else.
With consequences.
The absolutely mind-bending consequences for things like, well, time and space.
Okay, so if the speed of light has to be constant for everyone,
Mm.
something else has to give, right? Something we thought was fixed must actually be flexible.
Exactly. That's the core insight. If light speed is absolute, then our comfortable notions of time and space cannot be. They have to become relative. They have to depend on your motion.
Relative. Okay. Let's take time first. How does that work?
Okay, imagine you're an astronaut. Let's call you Alex. You're zooming past Earth in a super fast ship near light speed.
Okay, Alex the astronaut. Got it.
And back on Earth, your friend, Sarah, is watching you through a crazy powerful telescope.
So Alex is just cruising, maybe waving.
Maybe. But as Alex's ship gets faster and faster, Sarah back on Earth observes something incredible. Everything happening on Alex's ship appears to slow down.
Appears to. Like an optical illusion.
No, that's the crucial point. It's not just appearing slower. Alex's movements look slower. The clock on Alex's wall ticks slower. Time itself, for Alex, is passing more slowly relative to Sarah.
Whoa, hold on. So the actual physical clock on Alex's wrist is ticking slower than Sarah's identical clock back on Earth.
Yes, that's the mind-bending part. It's a real physical effect. We call it time dilation. The faster you move through space, the slower you move through time, relative to a slower observer.
It's not just perception. It's reality changing.
It's reality changing. It means time. Isn't this universal metronome ticking the same everywhere? Your now and my now can tick at different rates if we're moving differently.
So if Alex went on a long trip near light speed, came back,
Yeah.
they'd be physically younger than Sarah if they started as twins.
Exactly. That's the famous twin paradox, though it's not really a paradox, it's a prediction. And we've actually measured this effect. Tiny amounts, obviously, with atomic clocks on airplanes and satellites, but it's real.
Wow. Okay, so our basic idea of a universal now,
Mm.
that's maybe just wrong.
It seems that way, according to relativity, that single present moment everyone shares. It might not exist.
Okay, my head hurts a little. But you said space gets warped too. It's not just time.
You got it. The constant speed of light messes with space just as much as it messes with time. Remember Alex's spaceship speeding past Sarah?
Yeah, where time slowed down for Alex.
Well, Sarah would also observe that Alex's spaceship has shrunk. It's shorter in the direction it's moving.
Shorter, like squashed. So if it started like a long cigar shape.
It would look more like a flattened cigar. Maybe a space pancake if it goes fast enough. That's a funny way to put it.
This space pancake.
It's called length contraction. An object moving at high speed appears shorter in the direction of its motion to a stationary observer.
But Alex, inside the pancake spaceship, they wouldn't notice anything different. Their ruler still measures the ship as normal length.
For Alex, inside the ship, everything seems perfectly normal. The rulers haven't shrunk. The ship seems the same size it always was. But Sarah, watching from Earth, measures it as physically shorter than it was when it was sitting on the launch pad.
So it's relative. It depends on who's doing the measuring and how they're moving. It's not just like an opinion, it's a physical measurement difference.
Precisely. It's not a visual trick or perspective. It's about the geometry of space-time itself. There's no single, absolute, true length of an object independent of how it's moving relative to you.
Man, Okay, so time and space aren't this fixed stage. They're more like Play-Doh. They can stretch and squish.
That's a great analogy. Malleable, flexible, and it gets even weirder when you think about things happening at the same time.
Simultaneity?
Yeah, before Einstein, everyone just assumed, if it's 2 p.m. Tuesday here, it's instantly 2 p.m. Tuesday everywhere. On Mars, in another galaxy, this universal now.
Universal Tuesday.
Uh.
I like that. Sounds reliable.
It does sound comforting, but relativity just demolishes that idea. Whether two events happen at the same time depends entirely on how you, the observer, are moving.
How? Give me an example.
Okay, picture two lightning bolts striking the ground, one to your left, one to your right, quite far away.
Okay. Zap, zap.
Now, if you're standing exactly halfway between them, the light from both flashes reaches your eyes at the exact same instant.
You're right.
Right.
Equal distance, same speed of light.
Hmm.
Makes sense.
So you'd naturally say, aha, those two lightning strikes happen simultaneously.
Smells echo.
But now, imagine your friend Sarah is flying past in a super fast train right through the midpoint, just as the flashes happen. Because she's moving towards one flash and away from the other.
Oh, she'd run into the light from the one she's heading towards a bit sooner.
Exactly. And the light from the one she's moving away from would take a bit longer to catch up to her. So for Sarah on the train, the two flashes would not arrive at the same time.
So she would say they weren't simultaneous.
She would conclude they happened at slightly different times. And here's the kicker. Both observers, you standing still and Sarah on the train, are correct according to their own frame of reference.
There's no single right answer.
Yeah.
That Universal Tuesday is just my Tuesday.
Pretty much. Your now slice through reality isn't necessarily the same as someone else's now slice if they're moving relative to you. Simultaneity is relative.
Wow, okay. Need a moment. It reminds me of this. Okay, totally made up thought I had once. Imagine trying to take a selfie with two friends miles apart, right? You snap the photo. Looks like they both smiled at the same instant in the picture. But then you realize light takes time to travel. Maybe friend A finished smiling just before friend B started, but because of the distance, the light reached your camera at the same time for the photo.
That's actually a really clever way to think about it. It's not relativity at high speeds, but it captures that idea that perspective and the finite speed of light can mess with our perception of at the same time.
Yeah, just a little kitchen thought experiment. Okay, so time dilates, length contracts, simultaneity is relative.
Right.
Einstein basically turned physics into jello.
He certainly shook the foundations. And out of all this rethinking of space and time came, arguably, the most famous equation ever.
Yeah, I feel.
The MCPC. It emerged directly from special relativity, and it represents this incredibly deep idea. Mass and energy are not separate things. They are fundamentally interchangeable, two sides of the same coin.
Energy equals mass times the speed of light squared. That c squared part is huge, right?
All right. It's gigantic, which means even a tiny, tiny amount of mass, m, is equivalent to and can be converted into a truly enormous amount of energy.
And this isn't just theoretical.
Yeah.
It has had some pretty devastating real-world consequences. The sources mentioned Hiroshima, Nagasaki.
Yes. The atomic bomb is a terrifying demonstration of that equation, converting a small amount of nuclear mass directly into a massive destructive energy release. It's a very stark reminder of the power involved.
A sobering thought, definitely.
It absolutely is. But it's crucial to see the other side, too. That same principle, EMC hot, is what powers nuclear reactors, providing energy for millions.
Right, the potential for good, too.
And it's even more fundamental. It's how the sun shines. Nuclear fusion in the core of stars converts a tiny fraction of mass into the light and heat that sustains life. It's the engine of the cosmos, really.
So incredible power for creation, but also for destruction. Like Chernobyl, another example mentioned. It's all tied to that one equation.
It really encompasses both the promise and the peril locked within matter itself. Now, there's one more weird consequence of speed we should touch on, related to mass.
Oh, Mass changes too. I thought mass was just how much stuff is in something.
That's our everyday understanding, yes. But Einstein found that as an object moves faster, its mass actually increases relative to a stationary
It
observer.
increases. So the faster I run, the heavier I get. Not just feel heavier, but actually am heavier.
In a relativistic sense, yes. The effect is completely negligible at human speeds, but as you approach the speed of light, the object's measured mass starts to climb dramatically.
How high does it go?
It approaches infinity as the object's speed gets closer and closer to the speed of light.
Infinite mass. So you need infinite energy to push it any faster.
Exactly. Think about pushing something. The more massive it is, the harder it is to accelerate. If its mass is increasing as it speeds up, it gets harder and harder to push it faster. To reach the speed of light, you'd need an infinite force, infinite energy, which is impossible.
So that's why nothing with mass can actually reach the speed of light. The increasing mass is like a cosmic speed bump that becomes infinitely high.
Precisely. It's the universe's built-in speed limit for anything with mass. That's why we call it the celestial speed limit.
But light can do it?
Light particles, photons, have zero rest mass. They have energy, they have momentum, but no mass when they're standing still, so to speak, so they aren't subject to that infinite mass barrier. They just always travel at light speed.
Okay, so warp drives and faster than light travel. Probably staying in sci-fi for now.
Based on relativity as we understand it, yes. It faces some pretty fundamental hurdles built into the fabric of space-time.
Speaking of the fabric of space-time, all this bending and stretching, it leads to some really big picture ideas about reality, doesn't it? Like this block universe thing.
Ah, yes, the block universe. That's a major interpretation that flows quite naturally from relativity, though it can feel, well, strange.
How does it work?
It suggests that if simultaneity is relative, if there's no universal now, then maybe the distinctions we make between past, present, and future aren't as fundamental as we think.
Meaning.
Meaning that perhaps all of space-time, all of space and all the time, combined into one four-dimensional structure exists all at once, like a loaf of bread.
Both.
Yeah, where each slice is a moment in time, but the whole loaf, past, present, future is just there, a static block.
Whoa. So dinosaurs, me talking right now, whatever happens next century,
Yeah.
it's all equally real, just located at different coordinates in this block.
That's the core idea of the block universe interpretation, yes. Our feeling of time flowing might just be our consciousness moving through the slices of a block, but the block itself doesn't change.
That is profoundly weird. It completely clashes with our feeling of time passing, of the future being open.
It absolutely does. It's one of the most counterintuitive implications, and it raises huge philosophical questions. Is free will an illusion if the future already exists in the block? Deep stuff.
Definitely deep. Now, you mentioned Einstein wasn't totally alone in thinking about this stuff. There was another guy, Lorentz. Did he have a different take?
Yes, Hendrik Lorentz, a brilliant Dutch physicist. He actually developed some of the key mathematical equations before Einstein, the ones describing how lengths contract and time dilates.
Oh, so why is it Einstein's theory then?
Because their interpretations were fundamentally different. Lorentz believed these effects were real, physical changes happening to objects as they move through a substance called the luminiferous ether.
The ether, like an invisible jelly filling all of space that light waves traveled through.
Kind of, yeah. That was the prevailing idea before Einstein. For Lorentz, the ether was a fixed absolute frame of reference. So time dilation and length contraction were caused by the physical interaction of matter moving through this ether. Space itself was still absolute, three-dimensional, and time flowed universally. There was a true now.
So Lorentz saw it as a physical squashing and slowing caused by moving through something real.
Exactly. Whereas Einstein said, forget the ether, let's just assume the speed of light is constant and see what that implies. His conclusion was more radical. Space and time themselves are relative, they change depending on the observer. The effects aren't caused by moving through ether, they're woven into the geometry of space-time.
So same math, same predictions for experiments, but totally different underlying picture of reality.
Precisely. Einstein's view, without the need for an unobservable ether, eventually became the mainstream interpretation. It was seen as simpler, more elegant.
But I think one of the sources mentioned Lorentz's view isn't completely dead. It's getting looked at again.
That's true. It's sort of a minority interpretation, but there is renewed interest, especially among some philosophers of physics. They find the idea of an objective now and a flowing time appealing, and they explore if a Lorentz-like picture, maybe without the literal ether but with some preferred frame, could still be compatible with the evidence. They ask why these effects happen, looking for a deeper cause.
Interesting. But for this deep dive, we're just presenting both ideas, not picking a winner.
Absolutely not. The goal is to understand the different ways these same weird relativistic effects can be conceptualized. Both Einstein's view and Lorentz-inspired views have philosophical strengths and weaknesses. It shows how interpreting scientific results can lead down different paths.
Okay, got it. So let's try to wrap our heads around the main takeaways then. Time speeds up or slows down depending on motion.
Right, time dilation,
Things get shorter when they move fast, at least to an outside observer.
length contraction,
The idea of at the same time is fuzzy, depends on who's looking.
relativity of simultaneity.
And maybe the biggest one, mass and energy are basically the same stuff, convertible via e-Pipple-Weyken.
Mass energy equivalence. Yeah, those are the big counterintuitive pillars of special relativity.
So if space and time aren't fixed, if they're flexible and depend on us, the observers, what does that really mean? Could our feeling of now just be like one perspective on this bigger, maybe timeless reality?
That's the huge question relativity leaves us with, isn't it? It forces you to reconsider your most basic assumptions about the world. And honestly, what we've covered is just special relativity, mostly.
There's more.
Oh, yeah. General relativity brings in gravity as the curvature of space-time,
Hmm.
black holes, the expanding universe. It gets even wilder, but that's maybe for another dive.
Definitely sounds like it. Well, I hope this dive into Einstein's weird world has sparked some curiosity for everyone listening.
Okay.
If it has, seriously, dig into the sources, look up more info. There's so much mind-bending stuff out there.
Absolutely. It's a fascinating journey.
And hey, maybe next time you're stuck in that painfully slow meeting, just tell yourself you're experiencing some extreme time dilation. You're basically moving super fast
Yeah.
relative to something fun happening elsewhere.
Might not make the meeting shorter, but it's a fun thought experiment.
Exactly. A little cosmic perspective.